right? There's also an infrared and radio. She took the optical lab class. And having Emily in my class, she always tries to claim that it was a challenge for me, and that she was a challenging student. And in some ways she was, because she was always the brightest student in the class. And I really mean that. She had a real passion for understanding things. But I also really appreciated not just her inquisitiveness and the way she always kept me on her toes, but she also, along with her cohort, always made it very enjoyable in the class. They always had fun doing astronomy. And I think that's very important for productivity and creativity. So she wrapped up things at Berkeley, getting her bachelor's degree in astrophysics in 2005. And from there, she went on to get her PhD from Columbia University, where she studied with Kristen Minot. Upon completion of her PhD, she took a Sagan Fellowship for 2010 to 2013, splitting her time between first 2 years at Lunar and Planetary Laboratory, LPL, at Arizona, and then the final year at Princeton. After her Sagan, she had the Spitzer Fellowship for 1 year. And then she got the Presidential Fellowship at Michigan, and then that led into her current position as an assistant professor at University of Michigan, where I think they're very fortunate to add her to their faculty. One thing I'd like to mention is one of the activities she was involved in at Princeton was a program called the Prison University program. And first reaction might be, why would you bother teaching astronomy in prisons? And the unfortunate fact of the matter in our country is that about 1 out of 4 people of color in our country passes through the prison system, usually for nonviolent offenses. And one of the things that they learn in prison is how to become actual criminals. But the Prison University project actually provides them with another outlet or input and form of productivity while they're in prison. And this is actually one of the things that prisoners that are part of the program actually hold on to, like a life raft, dearly through their time. And it's one of the things that they value is their interaction with brilliant people like Emily and many other people at Princeton. And so I'm looking forward to eventually get involved with this here in the Boston area. Thank you so much for the time that you put into that program. It's a huge thing. And so today, Emily's not going to be talking to us about her time in prison. She's going to be talking to us about her favorite topic, which is planets, and more importantly, looking at these planets around other stars in 3 dimensions. Take it away.
Thank you. That is one of the nice introductions I have ever had. And thank you very much for inviting me to come to speak. Being willing to overlook my time in prison. And I like to start with a pretty movie because I figure the title slide is the place where you get to watch it the most, and it hypnotizes you before the talk starts, and so you've thoroughly appreciated the movie. This gives you some sense of what I do as well. I run 3-dimensional simulations of the atmospheres of hot Jupiters, so these crazy planets that are blasted on one side. And there's a lot of interesting things to say about them. And I actually decided that I'm going to take this opportunity to include some of the messy details as well. So hopefully that'll be fun. And thank you for inviting Jacob Bean to come talk a few weeks ago, because that's a nice kind of setup for my talk. He talked about some beautiful new data that's coming out. And so I'll just remind you a little bit of that and hope to evoke your memory of that. If you weren't there or don't remember it, you have a lot of in-house expertise, so ask around. They can tell you about it. I want to focus on the dirty details of modeling. So, here are my conclusions. I don't like outlines, so this is actually kind of an outline in disguise. But my conclusions are that as observations are getting much better, that means that we need to actually really be careful with our interpretation. Some of the earliest data were wonderfully motivating, but not super constraining. So now we're actually starting to have to deal with constraints, which is great. But this means that we really want to make sure that we thoroughly understand our models and know how trustworthy they are, how reliable they are, and which bits need work. And there are bits that need work. We're doing a good job, actually, but there's room for improvement, especially as we want to be able to test more detailed observations. And then, finally, I think that there's also hope for the future. I think there are new types of measurements that we can do, and I think that there's also a lot of power in combining multiple types of measurements, because you don't want to have a prediction with one observable. You want to have multiple ways that you can get at the actual physics at work. So you can either fall asleep or leave now, but I hope instead you understand why I have these conclusions. So let's start with what I think is an absolutely beautiful plot. We're used to showing plots like this in exoplanets, where we put up dots for all of the different planets. But the remarkable thing here is I'm not showing you number of planets versus date of discovery or mass versus semi-major axis. I'm showing you some physical properties of planets right here. And I'm allowed to do that in part because these are transiting planets, which are very valuable, as many of you know, because we can get a lot more information about them. So, for example, I'm showing you the mass in color on a log scale. This is about Earth. I'm showing you planetary radius, kind of relative to Jupiter. Here I'm plotting the equilibrium temperature. So for zero albedo, just based on how much flux the star is putting out and distance from the star, what temperature you would have. And this is all, of course, versus orbital period in days. So you probably can guess that all these black points without good masses are Kepler planets, of course. But you see that there's a lot of diversity here in terms of the temperature ranges that we're covering, which is related to the orbital period, although of course this spread is because we're around stars of different types. And we're finding, big gas giants, we're moving down to smaller planets, and this is really, really a very rich field for study, and only becoming more so. Now, the best and brightest exoplanets are always going to be the hot Jupiters. I'm just going to go out on a limb and say that. And this is because these are the easiest ones to detect, but also the easiest ones for atmospheric characterization. And so while there's a lot of interest in pushing down, and I agree, there's a lot of interesting things to do, we're always going to want to be able to study these planets first in order to figure out what we can do in terms of studying planets, to figure out how to study planets. And this creates a nice sample. They're all about the mass and radius of Jupiter. Their orbital periods, around 3 days, give them actually a range of different equilibrium temperatures. A couple more pieces of information that I'm sure you all already know. They're basically all on circular orbits. For this entire talk, I'm only going to be considering ones on circular orbits. They're assumed to be tidally locked, so they have a constant day side, a constant night side, and they can't have formed in situ. So these are also just interesting planets in their own right. We don't have anything like this in the solar system. And so if we want to say we understand planets, we better be able to understand all types of planets. And these ones are really weird and crazy in lots of fun ways. So, how are they fun and crazy? Well, what are the defining characteristics of a planet? If our goal is to go out there and say, not just that we know that these planets exist, but also to be able to say something about the planets, then we need to figure out what those important things we need to say are. And this goes into the different levels of complexity that we care about, right? So you can say maybe the planet's mass and or radius and its distance from the star, but that doesn't completely mean that you understand the planet. So, for example, a defining characteristic of stars is their mass, right? We all know and love this diagram, and we all know that if we know the mass of a star, we know so much about it. We know temperature, luminosity, radius, evolution, what's going to happen to it, all sorts of things. Now, I fully respect stellar astrophysics and realize there are many important secondary properties of these planets, many other interesting things you can learn about that. The mass is not the entire story, but it's obviously a defining characteristic. For planets, however, mass is not enough. We know this from our very own solar system, right? We have Venus and Earth, which are not too dissimilar, yet are very different places in terms of temperature, composition, and how much you would enjoy sitting there listening to a colloquium. Jupiter and Saturn, some difference, but why, right? Radius differences, density differences, ring differences. Now, Uranus and Neptune are an interesting example because they kind of both look like blue spheres, but if that's the only level that you're measuring them at, maybe you'd say they're fairly similar. Once you start to know more about these planets, you realize that having a very tipped obliquity is strange. It might tell you something about the formation and evolution of Uranus. And so what this means is that there's some kind of inherent differences between planets. But when we're talking about defining characteristics, we also need to take into consideration what can we observe. If we can only observe Uranus and Neptune insofar as their color, maybe we think that they're pretty similar, and maybe that's a fair statement to say. And maybe if we could never measure what's going on with obliquity tilts, we wouldn't consider that a defining characteristic. So in the game of exoplanets, this is not known. We know that there's a lot of diversity in terms of exoplanets. We don't yet really know either what is observable nor what are defining characteristics. So observers get to go out and do the very best that they can, and learn all sorts of new and interesting things and figure out new techniques and give us all the observables possible. And theorists have to go out and kind of allow for imagination and diversity in terms of possibilities and test models and figure out where the weak bits are and figure out which parts of the models, which parameters may never be constrained because we don't see observable consequences, and which things must be included. So now I'm going to very briefly skim over observations because I'm here and you can ask around if you'd like to know more. And I assume you've heard some before about transiting planets and the kinds of things you can measure. So we all know that we get to exploit this wonderful geometry, all sorts of different parts of the orbit, so that we can get information about composition and temperature of the planet. We also know that we're measuring different regions of the planet. So we're measuring the terminator, day-night separation here, day side there, looking at different wavelengths. We're measuring different depths into the atmosphere. One of my favorite kinds of observations is the whole rest of the orbit, where we get to measure different regions around the planet as different phases come into view. The quintessential example of that, my very favorite data, is this beautiful phase curve for HD 189-733b, where this was, I think, the first direct evidence that there are winds on this planet because, I'm not explaining this, I'm assuming you've already seen it, because the flux when the day side is pointing towards us is not aligned with when the substellar point. There's this shift. And if you invert the data, you have this hot spot that's shifted away from the substellar point, meaning winds are blowing it downstream, which is wonderful. My second favorite, or maybe they're equally favorite, type of observation is eclipse mapping, which has been done so far for one planet. As many things happen in this field, it was done by two different groups independently. And the idea here is that as the planet goes behind the star and comes back out from behind the star, the detailed shape of the phase curve can be inverted to tell you how much flux you were blocking at each time when the planet was slicing across the star slicing across the planet. And so you can invert this data, again, to make a map of what's going on the planet. So in this case, it's the same planet, right? So again, we see this nice shift. This time we actually do have some latitudinal information. Beautiful, absolutely beautiful. And to remind you again, not too long ago, you saw even more examples of this beautiful data where it's really leveraging the power of spectroscopy, looking at different wavelengths to probe different depths into the atmosphere. So for example, so this is also a phase curve. It's plotted as a function of time and of wavelength. And so you can see at some wavelengths, you don't have a lot of variation. And at some wavelengths, you might have more. And you see that also in these cases, the brightest region of the phase curve is happening before secondary eclipse at 0.5. And so this again means that you have this shifted hotspot, but this is kind of giving you an example, a reminder that as you look at different depths into the atmosphere, you might be probing different regions. And so here you really are starting to build up three-dimensional information about the planet, which is pretty exciting and beautiful and wonderful, but the interpretation's pretty complicated. So this is from that same paper that you should keep an eye out for. And what this is showing, because there's a lot of information here, as warranted by the data, is that these are for different times throughout the planet's orbit. This is when the day side is facing us. These are when the night side is facing us. And in each case, you can take the spectrum of the planet at that point, and you can fit a 1D atmospheric model to recover the temperature as a function of depth in the atmosphere. So when the night side is facing us, we're seeing cooler temperatures. When the day side is facing us, we're seeing hotter temperatures. So these are kind of independent 1D models for different regions facing us. Of course, different regions are not actually independent. And the other interesting thing of note is these dashed lines are the contribution function. So this is telling us which part of the atmosphere is being probed by these observations. And so this is another point of danger, is that this curve moves throughout the orbit. So we're observing at different wavelengths. This also means we're seeing at different depths into the planet as a function of time. So there's a lot of wonderful information here, but interpreting it starts to get a little bit tricky, because all these things kind of are overlapped and intertwined, and you have to think carefully about the best way to do this. Okay, so another important issue is that planets are not actually one-dimensional, turns out. That's kind of a theme of mine. And one thing that matters when we consider the fact that planets actually are three-dimensional, four-dimensional if you include time, is that planets have atmospheric circulation. And this is especially important to consider when we're focused on transiting planets, because remember, transiting planets, inherently by the way we're doing the observations, we're probing different regions of the planet. So at the very least, we need to understand whether a one-dimensional model is sufficient or whether we really need to account for the spatial dependence and variations around the planet. So I realize that atmospheric circulation is not like in the standard curriculum of most astronomers, so we're going to do a little atmospheric dynamics 101. So this is how the Earth works. For the Earth, we heat the equator more than the poles. And so hot air at the equator rises and flows towards the poles, cools, and returns. Except this picture is too simple, because we're missing one important property of the planet that significantly changes this circulation pattern, which is... Yes, of course. Good job. You all get A's. So because the planet's rotating, as the wind is blowing north, it gets turned, and so there's a limit to how far this Hadley cell can stretch. And this also has consequences for which direction the winds are blowing up in the atmosphere and along the surface. And this is not a very big extra step in terms of trying to understand how the Earth's atmosphere should work, right? We still have only said that we're heating the equator more than the poles and that the planet's rotating, and something about its rotation rate. But this gives us some predictions about what the wind pattern should be like. And we can compare this to actual data This is showing water vapor in the atmosphere for about a week, I think it is. And so this is kind of a tracer of what's going on with the winds. And you can see that we have a lot of the large features correct. Along the equator, we have this upwelling that's giving us all these clouds. We can see the direction of winds blowing along the equator matches our simple picture. At high latitudes, we have winds going in the opposite direction, which also matches our picture. These funny eddies here are the result of an instability that's triggered in the atmosphere that finishes the transport of heat from the equator to the pole. So that's kind of another little bit more complicated step, but you could say that based on just that kind of simple picture we created, we do a fairly good job of capturing some of the most important details of the Earth's atmosphere. And we can do the same kind of thing beyond the Earth. For example, on Jupiter, we know that it's different from the Earth in several ways, but we can also look at the flow pattern here. So I'd be surprised if nobody knew this, but when you look at Jupiter and you see these bands, those are delineating regions where the atmosphere is blowing in different directions, east and west, just to be clear. And so there's this beautiful turbulent flow going on here, and we can actually, through a little bit of more complicated physics that I'm not going to get into, you can say, well, okay, it's turbulent, so you're going to have features grow to larger scales because it's about 2D turbulence. And those scales actually have a preferred direction because you have the Coriolis force in the atmosphere and you have it varying with latitude, and so you're going to have a difference between north-south flow and east-west flow. And then you can say the length scale that you kind of expect planetary scale waves to start taking over from turbulence. Details, you can look them up. But the important part is that you can kind of create, through fairly simple arguments, what you expect the north-south extent of a jet to be based on the speed, the wind speed of the jet, and the strength of the Coriolis force. And you can plug in these numbers for Jupiter, and you get about the right number of jets. So again, we've been able to recover some important properties of the planet's circulation based on some simple creation, some simple understanding of what the atmosphere should be doing. Now, we can then leverage what we know to be the differences between a hot Jupiter and our own Jupiter to try to understand how hot Jupiters should be different. So they are hot, which means a couple things. One is that because you're heating the atmosphere so much, instead of having a thin radiative zone on top of a thick convective interior, like we do for Jupiter, you're going to have a thicker radiative zone, stably stratified zone, on top of the convective zone, which changes the nature of the circulation a bit. But also, just more simply, you kind of expect faster winds because you have a stronger force driving the atmosphere. And because it's hotter, you expect your radiative timescales to be shorter. So the atmosphere is going to react more quickly to the heating. The pattern of the heating is also important. Instead of heating the equator more than the poles, like we do on Earth, on Jupiter, with permanent day sides, we have a very different, strange kind of heating pattern where we're now trying to transport heat from the day side to the night side. And so we might expect to see a different kind of pattern because of that. But I think one of the biggest predictors that we can make is that because the synchronous rotation means that these planets should have rotational periods equal to their orbital periods, which means about a few days, the features on the planet should be much larger. The Coriolis force is weaker, so these jets and vortices can grow to be much larger. Instead of many little jets on Jupiter, we expect one or a few large jets on hot Jupiters.
What's the rotation period of Jupiter?
10 hours. So this lets us make some kind of initial expectations, but just based on this, I don't have a complete understanding of what a hot Jupiter should be like. And so to go beyond this, we need to start solving nonlinear equations, and so we do. And we do this through running three-dimensional general circulation models. There's several groups working on this. In all models, you have to make a choice about how you want to do the fluid dynamics of the atmosphere and how you want to do the heating of the atmosphere. Because it's the differential heating of the atmosphere that drives the winds, and so you need something to capture both bits. And you have a choice in terms of the level of complexity that you're going to use, the different assumptions that you're going to use, and it's very valuable that we have people making a range of assumptions, because then we can test our models, we can see which assumptions give different results, we can see which things might be valid, which things might not be valid. So this is great that we have all these different approaches. I have chosen to take kind of a middling approach where I'm balancing flexibility in terms of the types of things I can do to my model, do to my code without breaking, and still having enough complexity in the code that I think there's some amount of reliability, that I'm willing to believe most of what's coming out of my computer. Who was it who said, all models are wrong, some models are useful? My goal is to try to know which parts are useful. So for people who are a little bit more curious as to what this means, I'm going to show some equations. So these are the primitive equations of meteorology. So this is what's doing the winds. There's several assumptions that are made in here that take something like full Navier-Stokes and turn it into this set. For example, there's no viscosity. In the horizontal momentum equation, which is this, we basically have a balance between the Coriolis force. I know these equations don't look like what you're used to, so I'm kind of pointing out. Coriolis force versus pressure gradients. Now this looks funny because I'm using pressure as my vertical coordinate, and so a pressure gradient becomes a geopotential gradient, meaning that on a pressure surface, your GZ is changing. There's also, in the vertical, an assumption we make is that there's hydrostatic equilibrium. There can still, however, be vertical motion, but it all comes through the continuity equation. Horizontal convergence or divergence creates vertical motion. And then, of course, you need some way of coupling your dynamics to your heating, and that all gets thrown into the wonderful Q term. And this heating comes through how we choose to do the radiative transfer. We separate the visible wavelengths and infrared wavelengths, which is common practice in planetary sciences. And so the starlight, the visible light coming down through the atmosphere, first of all, the flux is attenuated based on the angle away from the substellar point. You receive less flux as you go farther away. And then it gets absorbed according to an absorption coefficient, single. So this is double gray in a sense, or exactly. And then there's also the angle appears here again to account for more optical depth. Similarly, the thermal flux, the infrared flux, gets absorbed and re-emitted based on the local temperature with a second opacity. And once we get to very high optical depths, we transition to using flux-limited diffusion, so it's now based on the temperature gradient, the same same thermal absorption coefficient. I should have had a second cookie. Okay, so as a reward for the equations, we now get to see another movie. So what I'm going to show you is kind of a standard result from one of my standard simulations of a hot Jupiter. And I'm showing you temperature in color, and the arrows are showing you wind. We're viewing the terminator of the planet, so the star is off in that direction somewhere, day side, night side. And what I'm going to do is I'm going to step you down into the planet, so moving to higher pressure, deeper into the planet. And so you can see that high in the atmosphere, you have a hot day side and a cold night side, and winds blowing from day to night. But as you get deeper into the atmosphere, the radiative times get longer, and so the winds are more able to change the temperature structure. And once you get very deep, you have a temperature structure, in fact, that's hotter at the equator and cooler at the poles. And you notice that here we have this big wide jet that we were expecting, right? Jet meaning all of the wind is blowing in the same direction. It's all going east around the equator. So there's another way to look at this, which is to take a couple of these levels and to pull them out into projection, where the substellar point's at the center and the equator is along the middle. And so here we are again, high in the atmosphere, hot day side, cold night side, flow from day to night. Near the photosphere, this is where we're starting to see the winds, the circulation actually change the temperature structure. And notice these wind speeds, the maximum wind speeds at these different levels. For reference, the local sound speed is about 3 kilometers per second. I'm going to blatantly ignore that fact and see if you ask me about it later. So I'm not the only person doing this. There are a bunch of groups working on this, which, as I said, is great. And we get general agreement between the models. We consistently see this pattern where the hottest spot is shifted to the east of the substellar point. This was actually predicted before the first observation and continues to be a common theme, although not all the time. And there's interesting reasons why, for example, this model doesn't look the same as the rest of us, and we can learn things through that. And to remind you what the observations look like, it's all consistent. So, am I done? No. It's not a finished project. It's not an answered question. And I'm going to explain to you a little bit why that is. So, one reason are examples like this. I think this is the best example of this. This is a very strange planet. This is Upsilon Andromeda b, and in this case it's not a transiting planet, but we still know where it is in its orbit, and so we can still do the same phase curve trick where we can see how much emission is coming from it when different parts of the planet are facing us. And so we know, and this was nice work by Ian Crossfield, we know that when the day side of the planet is facing us is not when the brightest region is. In fact, the brightest flux comes when about the terminator of the planet is facing us. Now this is surprising, not just because it's a much larger shift than we might expect, but because with a large shift, you would expect a smaller amplitude of variation. Because if the winds are able to efficiently move the hot gas that far away from the substellar point, that means that they should also be good at redistributing the heat around the planet, and so you don't expect such big temperature contrasts. But these are what the data show, at least right now for this system. So I think in this field it pays to be imaginative and pays to consider what other processes might be at work, what other variations we might want to explore. So one reason to keep working is weird data, and or, as I said from the beginning, just that data are getting much better. So we want to not just get the general features right, but really have some good confidence in our models. Also, there are a lot of messy details in these models that we don't always talk about, that I'm going to take some time to talk about. So I'll get to that one in a sec. And of course, another reason is that we're spending all this time on hot Jupiters, because as I said, not only are they interesting, but a great place to start, but we want to dip down into this, right? And so as we're starting to measure planets that are harder to measure, we want to make sure that we understand what's going on in the regime we can sort of do a good job at before we're pushing down in there. And that's not just observationally, but theoretically too. There are changes that happen, but we still are learning how to study atmospheres. And of course, this is especially important because the Kepler planets are not always so great for follow-up, but as we all know, TESS is coming, and this is going to give us many more planets that we can study, both smaller planets and more extensive variety. because we want these bright targets so that we can do the atmospheric characterization follow-up, because the defining characteristics of a planet depend on what is observable. And we're going to enjoy taking JWST and picking out some of these best ones to look at in detail. Stay tuned. Okay, so even the data we have isn't completely understood. The data's getting better. We have details to figure out, and we're also going to want to be able to extend our models. So, messy details. I figure, when at the CFA, why not air the dirty laundry? But to be fair, I want to start by airing some of Jupiter's dirty laundry. Because I think this is also an interesting perspective for astronomers, because we're not always aware of what we know about our own solar system. It turns out that just because something's right next door doesn't mean we fully understand it. This is an example. This is a fairly recent paper using a GCM, same type of model, to model Jupiter. In this paper, they tried a couple simple ways of heating the atmosphere. In one, they said, let's heat the equator more than the poles, as is the case. In this one, they said, let's alternate regions, kind of smaller, thinner regions of heating. And there are a couple of physical things that this could be kind of representing, but it's a different pattern of heating, right? In both cases, they got flow patterns that were similar, sort of. So what you're looking at here are average east-west winds. So you take the planet, you average in the east-west direction, and then you look as a function of pressure, depth in the atmosphere. And so this is showing you that you have regions alternating between eastward and westward. So you have these jets that we saw on Jupiter, right? Here's the problem. At Jupiter's equator, winds are blowing east. That's not the case in this model that uses kind of your best expected heating. You have to do this kind of weird heating to get eastward flow at the equator. And in this case, we're lucky, right? Because we can actually image Jupiter and track cloud features and see exactly what's going on. Maybe a little unsettling. Here's another recent paper modeling Jupiter, again with a GCM. This is 2010. In this case, they're using radiative transfer in the atmosphere, so they are heating the equator more than the poles. But what they're doing is at the bottom boundary here, sorry, for reference, this is the same kind of plot I was just showing. Red means eastward wind, blue means westward wind, and as a function of latitude and depth in the atmosphere, you're seeing the wind pattern. Here, they're imposing drag on the bottom boundary of the model. And this is because at pressures much, much deeper than this, you expect to eventually encounter the metallic core of Jupiter, metallic hydrogen, and you're going to have magnetic drag going on down there. And so including drag at the bottom here is a way of trying to capture the fact that you're going to have this momentum transfer throughout the planet. Notice in these two ones, where you have eastward flow at the equator, in both cases they're dragging off of the equator, but not actually at the equator. Whereas in these ones where there's drag all the way across, they don't get the right pattern. Now there's reasons to set it up this way, because if these columns, if these jets on Jupiter continue down as columns through the atmosphere, then the ones near the equator, if you can visualize it in 3D, I should have put a visual, the ones near the equator actually don't hit the interior. But once you start going up in latitude, they encounter the interior. But this is just a way of trying to capture that in a simple way, right? And again, they're cheating because they can compare to what we actually find on Jupiter in terms of what strength to set this at and how wide of a region not to drag.
Does the awakeness of Jupiter matter in any of these?
Not as a first order effect. Yeah. Okay, so I just wanted to be fair and say we don't have everything figured out for Jupiter itself yet. So cut us a little bit of slack. Or be very worried, because we don't have everything figured out for Jupiter yet. Okay, so hot Jupiters. What's some dirty laundry? Well, it turns out that the maximum wind speeds that we get in our models depend on how we set our numerical dissipation, which is maybe not surprising, but should give you pause for thought. This means that the maximum wind speeds are not necessarily something super predictive. We do think the winds should be fast, absolutely. Here, this is a plot of the maximum wind speed in a bunch of different simulations as a function of depth in the planet. And so you can see these simulations, for example, are all set up identically, same resolution, using different strengths. And so you can see, though, that there's some spread in the maximum wind speeds they achieve. Okay, maybe not so bad, except that we don't know what dissipation rate to set. The dissipation in the models is necessary, because otherwise you have buildup of noise on small scales. This is, people who do numerics know this. But the problem is that it's supposed to account for the fact that below our grid resolution, you have something dissipating. If somehow it goes all the way down in scale to molecular dissipation, it could be that, but really it's probably some kind of turbulence going on smaller scales. And we don't a priori know how to set that. There's not a good physical basis for it. You can kind of after the fact figure out what you should have done, and this is the way of doing it, which is you take your flow, you solve for a power spectrum. This is not cosmology, but I'm showing you a power spectrum. Power spectrum as a function of wave number, so again, large sizes, and you can see how much energy is contained at these different sizes in the flow. And this model, for example, this curve, you can see there's a huge buildup of noise on small scales. This is underdamped. Whereas this blue line has been overdamped. You're losing too much kinetic energy. But you only kind of know this by testing different dissipations and seeing which one works. The problem, though, is that these two plots are from the same paper doing this same kind of test. The colors on this one are the same as the colors on this one in terms of the dissipation rate that is set. The difference between these two plots is these are for atmospheres in which there's a single radiative time scale, and it's different between these two atmospheres. Which makes sense. If you have an atmosphere that's heating or cooling more quickly, you might expect that you need to use a different dissipation to properly capture what's going on. In hot Jupiters, we have radiative time scales going from very, very incredibly short at the top of the atmosphere to really long at the bottom. So choose your favorite level, choose your favorite value. You can look at it at a simulation and see whether you see lots of noise. You can do this kind of thing afterwards, but there's no clear choice for what to set. Yay. Okay. Why not talk about magnetic fields? That always makes things messier. Okay, we will. So, schematic of the planet. This is to remind you that we have different regions. This is not to scale. So we have our general circulation models probing the outer regions. You have all the way down to the rate of convective boundary. We have our photosphere within our general circulation model. Deep in the planet, as I mentioned for Jupiter, you expect a transition to metallic hydrogen. So you should have some ionization, some nice conductivity going on due to that. We expect that the planet should have a magnetic field that's anchored in that internal region. In the very high atmosphere, you have some photoionization, but some of these hot Jupiters are so hot that near the photosphere, you can actually get some thermal ionization, kicking off electrons from alkali metals. Still mostly neutral. This is non-ideal MHD. And I could give a whole talk about this, which I'm not going to. And it's a little late in the talk to go too in-depth, but this is really important for several ways. You may have heard about this whole ohmic heating thing. The basic idea, in case you don't know, is that because you have these ions embedded in the neutral winds, and the neutral winds are blowing around the planet kilometer per second speeds, you should generate these currents as they go through the magnetic field. The currents are going to flow somehow through the planet. They'll dissipate because it's finite resistivity and provide a source of heating somewhere in the planet. And this, if it's deep enough and strong enough, this could help to explain why some planets are bloated, because it's an extra heating source. But the winds are also going to feel drag because of this, because obviously the ions don't want to just get blown around through the magnetic fields. They couple well to the neutrals. It gets very complicated very fast. These are some of the earliest papers. You can look up the details. But this is a very messy detail that should almost certainly matter for the hottest hot Jupiters. Yay. Okay, but the situation's not completely dire. We can make progress forward. And as I said in my conclusions, the best way to do this is to combine multiple types of observations, and especially also to try to think of new things that we can measure, new ways that we can measure and use those. So one of these new ways that you can consult your own Jane Birkby about is measuring planetary Doppler shifts, which I think is super exciting. This might be my third favorite kind of observation. So this paper has some nice figures kind of demonstrating what's going on. I'm sorry I didn't have time to label this, but what you're looking at are very high resolution spectra taken from the VLT. So this is wavelength as a function of time moving up and down. You can see all sorts of wonderful Tollerk lines, and then there's some kind of corrections and some more kind of corrections, and then you have these beautiful data that obviously have information in them. Can't really see it by eye. This is an example of the information that they have in them increased by a factor of 10, so you can see it a bit by eye. What's going on is that this is a spectrum of the star, but the planet spectrum is also in there, and it's Doppler shifted relative to the star. Because of the planet's orbital motion, this is blue shifted and then red shifted during transit. And so you can pull that orbital motion out of the data. You can use a template spectrum to try to fit what the orbital motion is, and then this also allows you to recover a spectrum of the planet. So this is an example of, from the data and this template fitting, you have a nice 5 sigma result recapturing the systemic velocity of the system as well as the orbital velocity of the planet. Wonderful technique. Back in 2010, this was done for the first time to get the orbital motion, which is super cool and wonderful. But the part that I thought was wonderfully motivating and not at all constraining is that if you subtract off this orbital motion, they were left with a 2 plus or minus 1 kilometer per second blue shift. So not a measurement, but fascinating, because this, they said, okay, well, I guess that could be winds blowing from the day side to the night side of the planet, which would be blue shifted, right? And this is consistent because you're probing the low pressure regions of the atmosphere, high in the atmosphere, where, as I showed you, you have this pattern of flow from day to night. Wonderful! Except that the wind speeds we got were more like 10 kilometers per second. So why would you get a smaller value? So we thought it'd be fun to investigate this a little further. This is work I did with Eliza Kempton. And what I did was I said, well, maybe the winds are slower because you have magnetic drag on those winds. One of these messy complications that I told you about. And so I ran a 3D model normally, and then I ran one where I included a simple prescription kind of to act like magnetic drag. And so what you're looking at here are slices through the planet with your Doppler glasses. So you're seeing that high in the atmosphere, the winds are blowing towards you, and so you see a blue shift. This is during transit. And deeper in the atmosphere, you're seeing that transition to the jet that's blowing around the planet, and so blue shifted in one direction and red shifted in the other. A couple things to note about this plot, because I've had confusion. This is not to scale. This is only less than 10% of the actual radius of the planet. And also the observations are really only probing the outer shell of this at very low pressure. But it's still kind of a nice way of seeing it. And you can see immediately by eye that you have stronger blue shift here than here. Now, all of these models are run in the frame rotating with the planet. Turns out the velocities of rotation are comparable to these Doppler shifts from the winds, and so you need to include the rotation as well. Right? So one side becomes more blue shifted, one side becomes more red shifted. Right? Then, Eliza ran her nice detailed rate of transfer through my three-dimensional atmosphere, taking into account all of the local Doppler shifts, and created these very high-resolution simulated spectra. So the black line is a model where you don't take into account any Doppler shifts, and the 4 different colored lines are for a couple models with drag and a couple models without drag. Now you're not actually going to measure this, right? What you do is you take a template spectrum and you get a cross correlation. So she created a cross correlation, and you find a preferred velocity shift, and if you zoom in up here, what you find when you compare it to the Snellen et al. Result is that any of the models were for this non-measurement. But the models with and without drag are about the same separation as the current error bars. So if you can do a little bit better, you might actually start to be able to constrain something about this. And the reason why it's not 10 kilometers per second is because you only get the full effect when those winds are pointed directly towards you at the terminator. Once you're moving a little bit away from that, you're only getting a component of the velocity. Cool. What's the second kind of... Oh, yes. This is just one observation, though, right? So we want to compare multiple types of observations. So, for example, when you have drag in the atmosphere, you're going to change the pattern of flux emitted from the atmosphere. You're going to change your circulation. This changes your temperature structure. And so if you assume no magnetic field, or if you do a poor man's version of including some magnetic effects, you get no shift, or you get your traditional hot spot shifted east of the substellar point. And so what you might be able to hope for in the future is to look for planets where you have a telltale signature here, and a telltale signature here, and maybe a telltale signature in the radius of the planet, right? Because if you've got these magnetic effects, you might have that heating that bloats you up. So you want to try to tie these things together. I want to make sure to note that, as I said, this is the poor man's version. There are other people working on better versions of trying to model these magnetic effects using actual non-ideal MHD. It's very difficult to do, so all of these are very recent papers, and they get some different results. There's lots of different assumptions. This is definitely an area of research in progress, but really exciting, so stay tuned. Also, in addition to the radius, you might have a handle on the magnetic fields by considering how magnetic fields can affect the evaporation from the planet. I'm not going to say more than that because I don't have time, but look it up. It's interesting. Okay, very quickly, the second thing I want to note is that this Doppler shift technique is probing the wind speeds, but also the rotation rate. I said you have to include that. So maybe you can measure rotation rates this way. Eliza and I thought, and started working on it, and submitted a paper, and bam! First detection. I'm cool, though. I think this is exciting. So this is actually of the planet Beta Pic, directly imaged. You can separate out the velocity of the planet from the star. You can see that there's this planet signature. The dotted line is what you would expect for no rotation, and there's actually this rotational broadening. This thing's rotating really, really quickly. It's very exciting. We considered how you might do this for transiting planets, and we decided to frame this as, what if we test one of the most standard assumptions for hot Jupiters, which is that they're tidally locked into synchronous orbits? What if they're not? What if they're rotating a little more quickly or a little more slowly? It'd be cool to actually empirically constrain this rather than just assuming it. So I ran models going a little bit faster and a little bit slower, actually twice faster and twice slower than synchronous, you can see that there's different flux patterns coming off the slowly rotating model. There's actually a westward shift here, which is weird. But these ones have our standard eastward. So you have a difference, which is cool. You can also do the same Doppler shift technique, and we find that the preferred Doppler shifts for the slow and tidally locked ones are about the same, but in this case, the faster one has a shift of that, again, that tantalizing 2 kilometers per second. So in this case, the slow one looks odd in one way, and the fast one looks odd in a different way. So maybe this is something worth pursuing a little bit more. Whether or not hot Jupiters actually are rotating non-synchronously, once we get to longer period planets, it will be the case. So it's worth trying to figure out how these signals are intertwined, circulation and the rotation. It's also worth noting, this is for only one of the planets that we studied. I ran models for 2 different planets. The other planet, no difference, which means it's complicated, which is cool, because that means there's more to study and figure out why, in some cases, we might get observable signatures and sometimes not. Okay, and there's other groups working on this, figuring out what we can do with this tool. And okay, congratulations. You've listened to me talk about 3-dimensional properties, including temperature, wind speeds. I've even included magnetic fields. I've included rotation rates. And you're sitting there thinking, I know the data. I saw the data. You're really going to base all of that inference on those data? And I'm going to say, well, this goes back to the initial question I posed. What are the defining characteristics of a planet? And what is observable? If magnetic fields have a first-order effect controlling the circulation pattern on the planet, and therefore its thermal phase curves, for some hot Jupiters, then that is something that we have to include in the models, and that is a defining characteristic. So I don't know the answers to these questions yet, and I think they're very interesting questions worth looking into in much more detail. So stay tuned. And now you can see my outline. I posed this question. I talked about the kinds of things that we can measure, how hot Jupiters in particular are especially exciting of the transiting planets. We can build some good models, but they're not done yet. There's some dirt under the hood or under the carpet. We have details to figure out, and we can make progress. We can do better, and we can try to really constrain what the actual physical properties on these planets are. So stay tuned. Thank you.
All right, do you have questions for the speaker? Kasha.
Yeah, hi, thank you. Very interesting talk. So in the first part of the talk, you showed the phase curve of the hot Jupiter H2189 at various wavelengths. There was this really intriguing feature of the hotspot being well visible at most of the wavelengths, but there was some wavelength in the middle where this hotspot seemed to be much fainter than at other wavelengths. What do you think is going on there?
I don't know. So the question was, and some of the beautiful data from this upcoming paper by Stevenson et al., the multi-wavelength data, at some wavelengths you see kind of this prominent shifted hotspot, and in some wavelengths you don't exactly. And what that is saying is something about the pressure depths that you're probing, and something about either that wavelength doesn't have much emission at all, so you're not really probing anything, or at that wavelength, maybe you're probing deep enough into the planet that you're not seeing much temperature variation from around the planet. But that gets into the difficult task of knowing exactly what wavelength is probing which region, and that itself is dependent on the temperature structure, and so it's a very good question. I'd like to know the answer.
I don't want to discriminate which is the balconies, so just double check here. Okay. Over here.
Okay, yes. What is the role of the internal heating coming from inside the planet? And is this are all those effects depending on the age of the planet? And can be applied, for example, to brown dwarfs, companion brown dwarfs, and because they are.
Oh, these are all wonderful questions. So the question, series of questions, was how much does the heat from the interior of the planet matter? How does this relate to the age of the planet? Because that's going to change as a function of the age of the planet. And how does this maybe relate to brown dwarfs, which are self-luminous, and so it's all heat coming from the interior? So for hot Jupiters, for Jupiter, let me start with Jupiter, the flux coming from the sun is about the same as the flux coming from the interior, so they both matter. For hot Jupiters, you are 100 times closer, so you are 10,000 times dominant in the stellar flux than the interior flux, if it's comparable to Jupiter. We don't know what the flux coming from the interior is, but I don't imagine it's that much greater. So in the case of hot Jupiters, the atmosphere is really controlled by the exterior heating. For brown dwarfs, it's going to be exactly the opposite case, right? And so this absolutely changes the kind of circulation that you expect. And there's been a couple nice papers recently modeling brown dwarfs by Showman and I forget, I'm sorry.
Yeah, I was thinking about this ohmic dissipation idea. So particularly in light of the evaporation and evidence for evaporation we've seen recently with exoplanets, is it possible that the ions in the ionosphere could sort of evaporate and get trapped along the field lines and get accelerated around the planet's magnetosphere, and then have sort of electron, cyclotron, maser instability, and emit radio waves? And you can have a radio signal by these, because you see that with IO.
Yeah. Okay, so I don't, was that the end of your question? I don't
Yeah,
okay.
I just wondered, yeah, that's it.
So I don't know if I can repeat the entire question. It was basically about if you have magnetic fields and you have evaporation, might you expect some kind of interaction of the outer tenuous atmosphere with magnetic fields producing radio waves that you might hope to observe? People have absolutely thought about that. People have absolutely been trying to detect radio emission, like auroral kind of radio emission from, or any kind of radio emission from planets. There are no strong detections, basically just upper limits. There was a tentative detection a while ago. I don't know what happened to that.
Is that been surprising though? That they
No. That's the second part of the answer. It's not surprising because actually you don't know a lot of things that are relevant, like magnetic field strength, but making reasonable guesses, you don't think that you would be able to detect it yet based on current capabilities. But with exoplanets, if we know anything, we know not to think we know what to expect.
Well, Berger has been studying this in brown dwarfs, isolated brown dwarfs, and also Greg Callanan looking at this non-thermal emission. And they actually do see pulsed emission as these things have offset magnetic field poles in rotation.
Yeah. I mean, I would love to see it from an exoplanet because then you have some kind of constraint on the magnetic field.
Absolutely. I'll go back here for Bob and I'll come to Charles.
I have 3 complaints.
Oh, yay!
You didn't mention composition, and you're assuming all that. Second,
Yes.
it's awfully naive to assume you can have a 2-stream radiated transfer with
Okay.
gray atmosphere when you're actually showing spectra that have that wavelength-dependent structure.
Yes.
That's enough. Okay, I'll quit.
Only 2? Okay. So the 2 complaints were, oh shoot, I'm sorry, what's the
You
first?
forgot to mention composition.
Those are 2 related complaints. The first is I forgot to mention composition basically at all, and that matters a lot. The second is that I'm using simplified 2-stream double gray radio transfer when I'm showing beautiful multi-wavelength spectra that my model has no way of commenting upon because I don't have any wavelength dependence in my model. Wonderful complaints. I thoroughly approve. In part, so the composition is itself related to the wavelength dependence of radio transfer because, of course, if you change your composition, you're changing your opacities and how you're going to absorb things. Let's see, there's a couple of things I can say about this. One is that we don't know the detailed compositions of these planets. And so it's either something that you can have as a knob in your model and see what the effect is, or it's something you can ignore and leave out an extra knob in your model. And I've chosen to admit my ignorance. It does factor a little bit into the specific gas constant that I use, but I assume something dominated by hydrogen, because that affects the Hermite equations a little bit.
Could you install that knob and see how it affects the wavelength-dependent observations?
Well, so there's also how you're doing the heating of the atmosphere, which is the rate of transfer, and whether you have it wavelength dependent or not. Again, this is a case where I've chosen to kind of leave off some knobs and accept my ignorance. And I know, because there are people who are including this complexity, which is a good thing, that my models match theirs fairly well, which implies something about whether it's okay or not to do this more simplified treatment, which is a standard way of treating atmospheres in planetary science. So it's not being crazy, it's just being ignorant. And in terms of observables then, this means that what I'm focused on are kind of types of physical behaviors in the atmosphere, because I can't make wavelength-specific predictions unless I have somebody post-process my model, but that's not entirely self-consistent. So there's choices, and there's choices in terms of how I want to do flexibility, but I have reasons to believe that what I'm doing is not completely wrong.
Well, the standard answer is, when I get a bigger computer, I'll put in more frequencies and I'll change the compositions.
No, so there, as I say, there are models that include more complexity, but I actually purposefully prefer to leave it at kind of a more moderate level of complexity, because as you include more bells and whistles, it's harder to isolate exactly what's doing what in the simulation. And so it's just a different choice in terms of modeling, and it's, I think, useful to have models at all these different levels of complexity. But you absolutely want to be able to compare the more complex to the less complex to figure out what is reliable.
This is actually a follow-up to David's question. Is there any evidence in any exoplanet system for a planetary magnetic field?
Any evidence? Well, okay, so there depends on who you talk to. The question was, is there any evidence in any planetary system for any magnetic field?
Any exoplanet?
Any exoplanet, yeah. Yeah, in the solar system we know of a few, it turns out. Depends on who you ask. There have been some types of observations that people can invoke magnetic fields to try to explain, which tend to deal with what's going on with the tenuous upper atmosphere, either kind of evaporation, maybe evaporation rates, or there's some possible evidence of something like a bow shock, maybe, in the transiting system. While those could be evidence of a magnetic field, though, that's far from being completely definitive, and definitely far from telling you anything reliable about a magnetic field strength.
All right, well, let's thank Emily.
Okay.